So for instance, cesium, isn't it a transition element? Where is CS? Oh, nope, it's a 1A. Okay, so cesium's not a good example. Always form a +1 charge. Chromium, that's a good example. So the deal with chromium is, let's just pick on E for a minute. Okay, so E you need to do. And since it's chromium and it's found in the transition elements and it's not zinc, cadmium, or silver, you got to use Roman numerals with it, right? So you're like, all right, okay, I'm fine with that, but I need to use Roman numerals to reflect the charge. So you have to do a little bit of detective work. So for this one, you know that you are combining chromium that has a, I don't know what charge it is, and oxygen, you know, has a -2 charge, right? So this neutral formula said, and sometimes I'll tell students this different ways, but let's just try this way. We know that 2 CRs and 3 oxygens made a neutral formula unit. So that's to say that when I take 3 times -2, okay, plus 2 times I don't know what the charge is, I get 0. Does that make sense? I don't know. There's different ways to look at it. I know that Cr2O3 is a neutral formula unit. I know oxygens run around with a -2 charge. I know that collectively they're carrying a -6, those 3 together. Okay? So that means my chromiums, my plus charge, need to basically counteract the -6, or the 3 times -2. Does that make sense? So what's the question mark then? What's the charge of the chromium?
3.
+3. Very good. Okay, so it's a hard one to describe because it's almost like a little math, kind of little tiny problem. But to me, only once you can't name it until you do that.
Can't you just reverse the...
Kind of reverse crisscross? Yeah, that works. There's some snags, but that a lot of times will work, reverse crisscross. But however you do it, so it's chromium, Roman numeral 3, what's the last name? Oxide, yeah. Okay, so do those. And then the next part is, and a lot of these, especially, I get frustrated because teaching the subject of ionic compounds, which is what you just did. You guys, ionic. When you mix naming covalent compounds, which we're not covering right now, actually that's when you get to add the prefix that says how many of them are in your compound. So actually those are the ones that are crossed out here. Tricarbon disulfide, it's a covalent compound. Okay, so anyway, so these actually are, to me, even more reason, for instance, that you would want to break it out into its component ions. You know, you're going to want to memorize that ammonium, not to be confused with a neutral ammonium molecule, is NH4+, right? And dichromate is Cr2O7, 2 minus. It's actually 7. Okay, so you crisscross, and you know, then of course we need 2 NH4 units and 1 Cr2O7. Looks like a big formula for an ionic compound. That ammonium is one of those few polyatomic cations. So you don't have to write the component ions. I personally would, because what the heck, you got time. Okay. So on with covalent compounds. Okay, that's assignment slide. We'll get there. Actually, there are a lot of slides here that are just like, we already did that slide, and you're right. But I want to focus on, instead of where electrons are transferred to create a cation and an anion, okay, I want to talk about, and then a bond ... is formed between something that's positively charged and negatively charged. I want to talk about a case where electrons are actually shared. So atoms get a complete opposite. And that's what we call a covalent bond. So covalent bond is no transfer of electrons. Electrons are shared. They may not be shared equally, and actually the next few slides we're going to talk about electronegativity. And electronegativity is kind of like a tug of war. Whatever has the higher electronegativity is going to get kind of more of the share of, the more of the custody of the electrons. It's kind of like a divorce where you split the kids. It gets more custody of the electrons that are creating that, what we call covalent bond. So a covalent compound cannot have any ionic bonds in it. Covalent compound can only have atoms that are attached by electrons being shared. Remember, molecular compound is a synonym for covalent compound. So electronegativity, it's like a tug of war. You have atom A and atom B, okay, bonded together, and they're going to be bonded together by a pair of electrons at least, and the one with the higher electronegativity is going to actually pull more on that pair of electrons or more towards itself. Metals tend to say, you can have it, so they have low electronegativities. Nonmetals have high electronegativities. Okay, and so we already talked about electronegativity, and actually this is going to be a player when you come to draw the structure of a molecule or the structure of a polyatomic ion, like carbonate or sulfate, is the electronegativity is a player. So you're going to put the one with the highest electronegativity in the middle. Anyway, electronegativity increases that way and increases that way if you're talking about the group A elements. So here are the Pauling values, okay, of electronegativities. Those are all the chi values. And then we kind of went with the 1.7 or so. So you can do a subtraction. You can look up the Pauling value of the two atoms that are being joined together. Do a simple subtraction. Take the absolute value of that. And if the tug of war exceeds 1.7, electron's going to entirely be transferred. Less than 1.7, and electrons are going to be kind of shared, not necessarily equally. Okay, so actually this I printed out from my own reference. Okay, so these are the Pauling values again. These should just coincide with that other periodic table we saw earlier. So these are the electronegativity values, the Pauling values. That's the same thing there. And when we talk about covalent compounds, we're going to focus on these nonmetals. It's amazing the number of awesome compounds you can make from just all of these nonmetals bonded together. These actually are the atoms of life. Okay. So again, kind of a deja vu slide. Why does atom A and atom B want to get together in the first place? Well, it's because they both want to get a complete octet. Whether an electron is transferred or electrons are shared, they're trying to get a complete octet. So this is where, actually, this is probably a new slide. Oftentimes I'll kind of show students this kind of example of water. So the formula for water is 2 hydrogens and 1 oxygen. Okay. We're going to talk about valence electrons, and we're going to talk about drawing Lewis structures. So I kind of want to go ahead and introduce you to drawing what we call the Lewis structure of a water molecule. Okay, so hydrogen, and this is actually when I draw Lewis structures, I'll kind of address the element and then I'll say something about it as that hydrogen exists in that molecule. There are actually 2 hydrogen atoms, okay, and hydrogen is the simplest element of all. It has 1 proton and 1 electron. So it has 1 valence electron, so I'll go ahead and put 1, okay. So collectively there actually are 2 electrons that are brought by both of them. I'll go ahead and put oxygen down here. There's 1 oxygen atom. And with regard to, these are going to be valence electrons. We talked about electron configurations. We talked about valence electrons are the last added, the highest N. And we said you don't have to think too hard if you have a periodic table handy to know how many valence electrons any element has, because it's the group number. So oxygen, we kind of creep up, and it's actually in group 6A. So it has 6 valence electrons. I don't think I'm necessarily going to worry too much about its whole pot of valence electrons. Pot of valence electrons. I'll be referring to that if we get to it later. But what I do want to emphasize is how this water molecules look like Mickey Mouse. Okay, if the hydrogens are the ears and the oxygen atom is kind of the face of Mickey Mouse. They are what we say bent, and we're going to talk about why those hydrogens kind of repel from. Why don't they even out? Why do they do that? Well, there's a reason for it. But when we talk about those three atoms getting together, that's the point of this slide, okay, is if we go ahead and let those 6 valence electrons around the oxygen atom be represented as X's. Okay. So there's my oxygen, there's my 6 valence electrons. Then when a hydrogen shimmies up to the oxygen atom on either side, I'll go ahead and show the hydrogen atoms are going to have valence electrons are going to be represented as dots, kind of big dots. So what this is talking about, okay, and I'll go ahead and kind of maybe a little bit getting ahead of myself, but anytime you see a structure like this and that dash right there, that is actually representing a pair of electrons. I might have this backwards. But this is my whole point. Okay, so those 3 atoms, those water molecules, are joined together by actually what we call covalent bonds. Now, one of the rules for covalent bonds, there's a lot of them, but one of them is that electrons are shared, not transferred. But the other is that they come in pairs, like we have bonding pairs. There's a bonding pair right there. One rule is that the electrons can come from both from the same atom, or in this case, one electron's coming from hydrogen, one electron's coming from oxygen. They have joint custody sharing. So that's a lot of time spent on talking about how electrons are shared in covalent bonds, specifically between the oxygen, the hydrogen, and water. So of course, every rule was made to be broken. So when we talk about the octet rule, which, you know, 8, we all want what we call NS2NP6, kind of rare gas configuration. There are some exceptions. So of course, the symbol for boron is B. And when you see boron in a Lewis structure, okay, or you work with it, you're actually going to see it happy with 3 pairs of 2 or 6 electrons. The other thing, and in your homework you're going to run into this, another exception to the octet rule, and I'll just go ahead and put the symbol X for some element. It's quite possible in its Lewis structure that instead of its final Lewis structure, when it's bonded to other stuff, instead of having a complete 2, 4, 6, 8, a complete octet, sometimes instead of 8 it will have 10. It happens. Okay, and sometimes it will have 12. So that symbol represents some element. Okay. 10 electrons, 12 electrons. It's called an expanded valence, and it happens. We're not on a test. I probably won't give you a situation in which an atom has an expanded valence, but it happens. Okay. So kind of the simplified version, that's all I know, of what's called the valence bond theory. Okay. Valence bond theory is talking about covalent bonds, talking about electrons being shared between 2 atoms. So I brought some examples here to kind of help show what's going on. We're going to pick on this. This actually is, let's see, methane, ethane. This actually is C2, so those black things are carbon, and these are hydrogens. So we have C2H6. Okay, these gray things are covalent bonds. Okay, so some rules about covalent bonds. So let's pick on this covalent bond between these 2 carbon atoms. This is kind of wild. Okay, So we said that carbon has, each carbon atom individually has what we call atomic orbitals. Those are the boxes, right? Atomic orbitals, they're organized in subshells. Okay, atomic orbitals. So carbon A sends out one of its atomic orbitals. It's like it does it purposefully, right? Carbon B sends out one of its atomic orbitals. Okay, so this is carbon A, this is carbon B, and actually kind of where my elbows are is like the center of the carbon, or the nucleus. And these things that I'm swinging are the atomic orbitals of A and the atomic orbital of B. So basically the atomic orbitals overlap, okay, and they create what's called a bond orbital between these two atoms that are going to be joined together. Let no man put us under, right? Okay? So this right here is your bond orbital. That's the gray thing. Every bond orbital needs 2 electrons hanging out in there. Every bond orbital, every covalent bond orbital. Okay? And there's a degree, actually, these covalent bonds come in different strengths. And literally, sometimes there's more overlap and sometimes there's less overlap. And kind of intuitively, if they're just barely overlapped, actually it's a weaker bond. There are a lot of overlap, it's a stronger bond. Okay, so each bond orbital must have exactly 2 electrons. It can't have any less and it can't have any more. So I kind of like the little water molecule we looked at a minute ago. Okay, because we kind of really showed that dash we're used to seeing that connects the the middle oxygen atom with the 2 hydrogen atoms. That dash has 2 electrons there. That's a covalent bond. Okay, and this is kind of fun. We talked about kind of the up-down spins. Where are you ever going to use that again? Well, those electrons actually that are occupying that bond orbital have opposite spins. And this down here, I told you, our example of water, actually, 1 valence electron was kicked in by each of the hydrogens to make that bond, and then oxygen donated 1 of its valence electrons to make the electrons hanging out in the bond orbital. Doesn't have to be that case, but it can be. All right. So carbon is great at, I know there's a reason for this, it's not coming to mind right now, but carbon is great at forming more than just what we call single bonds. So if you've been around a while, you've probably seen carbon bonded to carbon that looks like this. That's called a single bond. Double bond is carbon with 2 dashes. A triple bond is carbon with 3 dashes. You've probably seen that before. But now what I'm hoping you're starting to think, that convention actually, each dash is a covalent bond. So if you see this on a structure, I'm hoping you think 2 electrons, 4 electrons, and 6 electrons. Because each dash is a pair of electrons. Okay? Gotta love carbon. Covalent bonds come in 2 flavors, vanilla and chocolate. No. Okay. Okay, covalent bonds. Covalent bonds, a pair of electrons being shared. Okay. There is the sigma bond. Okay, sigma bond. Greek letter sigma. And actually those are a good way to automatically think of them is that, like the slide says, they are the primary bond. They are what I usually say, the first to arrive. Okay? They're the first to arrive. And it's kind of funny, you'll see why. But actually, these are your meat and potatoes. You have to have meat and potatoes before you can have dessert. Unless you're like my grandma. As the older she got, the more she's like, let's just go for dessert. Like, cool. Okay, so actually, I'll pick on this C2H6. As I draw this Lewis structure, there's the 2 carbon atoms. Okay, black. And here are the 3 hydrogen atoms around each carbon. Okay. So honestly, let's see, how many are there? 7? All 7 of these bonds are sigma bonds. All 7 of them. Oh. The other thing, they're the first to arrive, they're the most important, okay? And we can think of basically that pair of electrons that are participating in that bond orbital as lying between the nuclei of the atoms they're connecting. So, for instance, we didn't pick on these where the carbon atom connects to hydrogen atoms. Okay, that is a sigma bond. It's a covalent bond, but more specifically, it's a sigma bond, first to arrive. And the electron cloud, okay, is right here between the nuclei of the hydrogen atom and the carbon atom. Because that's different than the chocolate one I'm going to show you. All right. So if 2 atoms are bonded together, which is what we're talking about, atoms being bonded together, there at least has to be a sigma bond. And if there's room, there can be a pi bond. So pi bonds are these other ones to arrive, to give the atoms a complete octet. So do you see where get it pi is dessert? Okay, so these are dessert. Oh my goodness. And I can never spell dessert. Is it 2 S's? Okay. So examples of pi bonds are actually, I brought some here. I brought both of these, where you have a carbon double bonded to another carbon, and if that's the case, instead of each carbon having 6 hydrogens, we'll kind of talk about why this is, but they only have room for 2 hydrogens. Sorry, 6. I meant instead of each carbon having 3 hydrogens, they can only have 2 hydrogens. Okay. So as I've drawn that, okay, here between the 2 carbon atoms, the first to arrive is the sigma bond, and the second to arrive is the pi bond. So there's, what, 4 electrons between these 2 carbon atoms? Yeah, that's how that works. So, C2H4 looks like this. Okay, carbons, C2, and each of the carbons are singly bonded to hydrogens. So that's a single bond hydrogen, single bond hydrogen, single bond hydrogen. All right, there's the single bond between the 2 carbons. What this says is that those pair of electrons, now this kind of blows my mind, those pair of electrons that now are participating in a type of covalent bond we call a pi bond, okay, they can't be here because that's where our bond electrons of the sigma bond are. So where they are is above and below the plane. It's like a hot dog. Okay, so these go together as one pi bond. So that's cool. I'm like, electrons, you are so smart. So the other structure I brought today actually is carbon triple bond carbon. And of course there's 6 electrons connecting these carbon atoms. And we'll see probably why this is, but if that's the case, instead of having 2 hydrogens off of each one can only accommodate 1 hydrogen. So the way you would tally this up is the first to arrive, and it doesn't have to be the bottom one. It seems like it should be the middle one. I don't know. It doesn't really matter. But your first one is you have 1 sigma bond, and you can't have 2 sigma bonds, so the other 2 are pi bonds. Okay. So we have 6 electrons being shared here, and of course we have 4 electrons being shared here. It's a wonderful thing. Okay. So, this is one of those where it seems like they should come up with a different term. because we're familiar with, and I know valence electrons are kind of connected with the valence of an atom, but it's a different concept. So valence electrons, you know, we said you can look at the group number to know how many valence electrons an atom has if it's a group A element. The valence of an electron, sometimes you'll hear me talk about the valence of an electron is the number of times it reaches out. And I'll try to explain what I mean. Okay, it's the number of times an atom reaches out. I guess that's where I should have put my quotes. Reaches out, okay, in sigma and pi bonds. Sigma and pi bonds. And actually, I'm going to squeeze something up there. I'm going to put it's the expected. There are definitely exceptions to the expected valence of an atom. And so what is that number? Well, if it's a main group non-metal, okay, then what you do is you take the group number. Sorry, you take 8 minus the group number. So for oxygen, and actually, oops, sorry, not sigma, for the element oxygen, okay, it's actually in 6A, okay, so you take 8 minus 6, and of course you get 2. Okay, so we expect oxygen to reach out twice. Those examples you have in your notes, if you jotted them down, for carbon is a group 4A element, so actually 8 minus 4, okay, is equal to 4. So we expect, and that's a better example to go with right now, so we expect carbon to reach out 4 times. So actually on those simple structures I showed you, carbon is the total number of sigma and pi bonds that carbon has, each of those carbon atoms have in all these examples is 4. Okay. I forgot to show you this one. Dang. Okay, this is a triple bond. This is carbon, triple bond, carbon. So the first to arrive, that's the gray, that's the primary sigma bond. And notice now that we actually have 2 pairs of pink and purple. So each pair of pink and purple, pi bond, pi bond. So we have sigma, pi, pi. Okay, and this is actually the shape of this molecule without the purple and pink. Actually, this is the shape of this molecule without the purple and the pink. And this is the shape of this molecule because it has no invisible purple and pink. Okay, so 8 minus the group number. So for carbon, we expect it to reach out 4 times, nitrogen and phosphorus 3 times, oxygen and sulfur twice, the halogens once. And hydrogen only wants to reach out once, and boron only wants to reach out once. So just to kind of emphasize what I mean by the valence of an atom, I'll put the word expected up there. Okay, what it means is the number of sigma and pi bonds. All right, so that can come in handy when you're trying to kind of assemble, on a piece of paper, trying to assemble atoms into a molecule that makes sense. So these are the Lewis dot formulas for the atoms. And those, remember, those dot, dot, dots are the valence electrons around carbon, nitrogen, oxygen, fluorine, and neon. So we kind of looked at this before, that, and I said it's almost like you're playing cars, kind of pushing them up to, these are garages, okay. But this is actually kind of giving you a sense of, notice there are 4 spaces, 2 parked cars around a carbon atom, 3 spaces around a nitrogen atom, 2 spaces around an oxygen atom, 1 space around the halogens. And the expected valence is 4, 3, 2, and 1. All right. So I think we are going to be able to get to one example of just drawing what's called a Lewis structure. But I know for sure I'm going to show you some examples of some Lewis structures. Now, Lewis structures need to depict all the atoms that are stuck together, right? Makes sense. The Lewis structure is going to use a dash to represent a covalent bond, pair of electrons, every dash you see. The other thing, though, is Lewis structures are going to show you anytime there are what we call lone pair electrons. Lone pair electrons, you're going to hear me call them dot, dot. Okay. Lone pair electrons are players. Lone pair electrons are great at giving shape to a molecule. Lone pair electrons are generally invisible. That's the way I think of it, but they are there. Okay. So when we come up with a pot of valence electrons, our pot of valence electrons will be distributed around our Lewis structure, and either they will be participating in single, double, or triple bonds, or they will be dot dots, lone pair electrons. So just like we talked about before with those simple Lewis structures of the elements, whenever you see the symbol of an element, think nucleus and think non-valence electrons. And anytime you see a dash, think the primary, or think a pair of electrons are shared. Okay, we talked about that. All right. And know that the whole north, south, east, west thing, everybody's Lewis structure can really kind of look different. Okay, because you know where you park your car can be different. Okay, but it's kind of handy, kind of with the 4 directions. 4 times 2 is 8 electrons around most atoms to make them happy. Lewis structures obviously are drawn on paper, so the paper cannot necessarily depict 3 dimensions. So like today I brought, this is the C2H6. Okay, on paper, there are ways to actually, especially in organic chemistry, we kind of try to draw on paper things coming out of the paper and kind of into the paper, but just the way I stick draw them, you can't really tell. But after Thursday's lab, we're going to talk about how you can basically, in your own mind, lift off a paper and kind of make it 3-dimensional. All right, so let's pick on a few Lewis structures. So the ammonium cation that we recently talked about is NH4 plus 1, right? Ammonia is the neutral molecule. So one of the things, this is a final Lewis structure, one of the things about final Lewis structures is we should be able to look at them and make sure that everybody has a complete octet, okay? Or in the case of boron, 6 electrons, okay? In the case of hydrogen, 2 electrons, because when hydrogen has 2 electrons, it's what, like helium. So we kind of end up with drawing these kind of Venn diagrams. I think they're kind of Venn diagrams, maybe not, okay? Where, those 3 external atoms, those 3 hydrogen atoms, notice that they each individually have 2 electrons, so they're like helium. And we could go ahead and draw a circle around the nitrogen, okay, and it's got custody of 2 electrons there, 2 electrons there, joint custody, right? 2 electrons, that's 6. Now this up here is a pair of lone pair electrons. And when we start from scratch drawing our Lewis structures, you're going to see that actually they came along with the pot of valence electrons that was brought by nitrogen and the 3 hydrogens. All right, formaldehyde. Again, 3 atoms. And if we kind of take a check on, are they all happy? Okay, the hydrogens are happy. Hydrogens never want to have, see how it's got 2 electrons? Because each dash is 2 electrons. It never wants more than 2. Okay, the carbon atom, it's got what? There's a sigma bond, sigma bond, sigma bond, pi bond, right? So we have 8 electrons there. And then around the oxygen atom, it's got this double bond with the carbon, so it has 2, 4, 6, 8. It's actually got 2 dot dots, two pairs of lone pair electrons. So it has what we call a complete octet. One of the things we draw Lewis structures of are these polyatomic ions. So the halogens, like chlorine, are great for combining with oxygen. The fewest numbers of oxygen it can have is 1, so of course we call that hypo, and it in ite. So this is hypochlorite. And notice the complete octets. 2 electrons are shared there. Okay, so they each have a complete set of 8. Not to mention, each atom has these like invisible 3 pairs of 3 pairs of lone pair electrons. So 6 lone pair electrons skirting out. Okay, so this is kind of a reminder slide. That boron doesn't want 8, it wants 6. And also to remind you that even though in your homework you'll have these where you're drawing Lewis structures, and I've warned you which ones, where you have an atom that has more than 8. It has what we call an expanded valence, 10 or 12. And to remind you, it's going to be a lot of reminder, to remind you that the reason that electrons are shared or transferred is because atoms want to get that rare gas configuration, otherwise known as a complete octet. Okay. So we'll be hitting this hard on Thursday, but I'll just kind of step you through these actually steps 1 through 5. And we're going to pick on formate. So formate has, what, 4 atoms, 1 hydrogen, 1 carbon, and 2 oxygens. Notice that it all runs around with a -1 charge. So it's a polyatomic anion. So when I said we come up with a pot of valence electrons, it's kind of like what I said was started with the water before. There's 1 hydrogen atom, it has 1 valence electron. 1 carbon atom, it has 4 valence electrons. 2 oxygens, and oxygen is in group 6A, so each of them have 6 valence electrons. Okay, so we're kind of coming up with our pot of valence electrons. Now, since it's charged with a -1, we have to kick in 1 more electron, just because the -1 charge. So if you add all those up, you get 18. So that is our pot of valence electrons. And that needs to be represented on our final Lewis structure. Pot of valence electrons. Can't have any more, can't have any less. So the next step, as you might imagine, is to kind of come up with, well, how are those darn things arranged? And in your notes, when we do this on Thursday, I'm going to emphasize this, and it's in your write-up, but you put the lowest, the atom with the lowest electronegativity in the center. Okay. And electronegativity, make sure I got that right, yeah. I think I told you wrong a minute ago. But electronegativity, it's low, carbon is lower than oxygen. Why? Because electronegativity increases from left to right. And while I'm at it, in case I forget to tell you Thursday, hydrogen never wants to be in the middle. It's all about the middle. We're not going to get too complicated in drawing Lewis structures. There will be a middle. Either that or there will only be 2 atoms. So on the next slide, we need to go ahead and say how many electrons do we have left. But can you see on this slide we have, this is a preliminary drawing. We have 1, we have 2, 4, 6. We have 6 represented there. Okay. So in other words, 18 from our pot minus 6, we have 12 we need to do something with. And you're going to see that we take those 12 and we distribute them amongst our terminal atoms. And if you kind of look at, we chose carbon to be in the middle because it has the lowest electronegativity. And from that, then oxygen and hydrogen are terminal atoms, but hydrogen's done. Okay. Then one last step, well, kind of. So one last step that may or may not, the 5th step, may or may not have to apply, is we check the central atom, which is carbon in this case. And can you see where carbon only has 2, 4, 6? Carbon only has 6 electrons. Oh. So it's called convert, we are actually, and we could choose either one of these oxygens, but we are going to swing or convert one of those lone pair electrons. We're going to make it do double duty. Well, it's no longer going to be a lone pair electron. We're going to swing it in and make it a pi bond. We could have swung it from either oxygen. We just swung it from the north one instead of the east one. But if you compare this structure with the previous structure, one of those lone pair electrons swung in. Now that central atom's very happy. It's got a complete octet. And that would do it for me today. So the assignment at the end there is going to be due on,
Friday.
yeah, seems like it should be Friday. Yep. And Thursday in lab, you're going to get like a sheet like you did for lab. So you can turn that in on Monday for a lab credit. That sounds good.